Good morning, ladies and gentlemen. This is Mr. Nomo TP from Lerado Tando. Today I'll be responsible for the exam preparation of electronics. So the purpose of this whole presentation is to prepare the matriculant who will be writing electrical technology under specialization of electronics on Friday the 11th of December 2020. So with that said, I would like to wish all the matriculants across the country the very best on their paper of electronics. So with that said, let us start with the presentation. So our question paper, normally it consists of 5 questions, the question paper of electronics. So first question being the occupational health and safety, which will consist of 8 marks of our question paper, on the question paper of 200 marks. Then the second question is RLC, which will be, normally it's 42 marks. Then the third question, it's semiconductor devices, which normally is 38 marks. Then followed by the 2 main questions that we have that are the heaviest. The first one being switching circuits, which takes the weight of about 58 marks. Then the last one will be amplifier, which also takes up about 58 marks. So with that said, let's proceed with our presentation. So let us see the structure of the NCS examination paper. So the first one, it says the grade 12 revision electronics. Structure of the NCS exam paper, an important point to remember. The paper consists of 6 compulsory questions, but in the case of electronics, it will be 5 questions. The weight of the question paper is as per on the table below. It is important to remember that this paper is out of 200 marks, and the time given is 3 hours, which will be 200 marks. So 200 marks in this case will be equal to 180 minutes. So before writing, it is important to ensure that you manage your time properly when writing any test or exam. You do not want to run out of time because of bad time management. The following rough guide will help you manage your time a bit better. 1 mark, 1 minute. If a question paper of out of 10 marks, do not spend more than 10 minutes on that question paper. Try to start the easiest question and work your way up to a more difficult question. So that simply means start with a question that you feel more comfortable with. Then and you'll see how you go with the rest of the question, so as to save time with things that you may not remember at times. All question and sub-question must be kept together. Do not mix questions. By the phrase "do not mix question," it simply means when you write question 1, write question 1 up until you finish it, rather than having question 1.1, question 1.2, then you'll have 1.3 in the middle of question 3 or question 1. That is not acceptable, people. It is important that you read all instructions slowly before you start answering any questions. Please, people, when you get to the exam room, make sure you get there 30 minutes early so that you do away with all the admins that you've got to do, and you read your question paper carefully before you can start. In that way, you get to analyze the question paper, the questions, so you will save a lot of time by doing that. Also, please note that you must receive a formula sheet with every test or exam you write, covering at least the topics of the test or exam. So every question paper that comes will come obviously with the formula sheet at the back. The questions are asked in such a way that will differentiate in terms of subject knowledge. It might start with easy questions and end off with more challenging questions in the different question papers. So I'll skip this part. Okay, let me just go to it a bit. Basic skill linked to the subject examination guide. The following skills are measured in the paper: ability to follow instruction, identify labels, marking, drawings, diagrams, schematic, representative. So you know when you have to write electronics, you know you're going to identify, you're going to draw and label the sketches, the waveforms. So you must be able to do all those things. Plotting and interpretation of the graphs and the data. Working out and interpreting calculations. So in our subject, the calculations are a bigger part of this subject. So make sure you practice those calculations. Organizing and recording, categorizing data. Extraction or manipulating or evaluation of data. It is important that you have your own scientific calculator that you might use it. Never borrow a calculator for any examinations. Topics NB. The mark allocation will indicate how much information you are required to provide in your response when answering a question. People, you cannot answer a question of 6 marks and provide 1 fact. So as it has been said, the marks on the question will tell you on how much you got to write or respond to a question. So we'll be brushing off the occupational health and safety and RLC, then we'll go a bit into depth on switching circuits and amplifier. So here we'll just brush a bit. This type of a question paper that you find here, the type of question that you find here, this is a very open-ended type of topic. Learners need to ensure that they read every question very carefully with understanding. Remember, when it comes to occupational health and safety, this is the question that when you are in grade 12, this must not be a very difficult question, because from grade 10 these questions have been asked. So learner must make sure their answers are short and to the point. They must remember the examiner marker must understand what they are trying to say in their answer. Be as clear as you can so that whoever will be marking your script will understand what you are saying, and straight to the point. Many learners do not look at the mark allocation of questions and only give 1 fact for 2 mark questions. Like I've said earlier, the mark allocation of your question will guide you as to how many points that you've got to write when responding to a question. If it's a question of 2 marks and it needs facts, please provide 2 facts. If it's a question of 3 marks, 3 facts. The duty of the employer and the employee in the workshop is very important, and learners must know it. The following concept, which was also done in grade 11, is not always answered well. Unsafe actions. This refers to specific action that lead to an injury or cause damage. Then unsafe conditions. This refers to conditions that might lead to injury or cause damage. Risk analysis. You might be able to distinguish between quantitative and qualitative risk analysis. Work ethics reflects on how work ethics improve teamwork. Occupational health and safety. An accident. What is an accident? As it's saying there, an incident arising out of worker and resulting in a personal injury, illness, or death of a worker. Risk analysis. Risk analysis is a process that will inform workers in the workshop about good housekeeping and safety practice. Dangerous practice. Activities that have some form of risk hazard when performed in the workshop. The use and misuse of power tools. When working with power tools, you must observe safety rules to avoid wearing loose hanging clothes, and you must take in your long hair. The correct use and handling of hand tools. Tools must be carefully functional and used for the purpose for which they were made for. The etching of PCB. Etching is used by making use of chemical and acids. The chemical can be harmful as they could damage your clothes or even be dangerous to your skin. 5 steps of risk management. We've got diagnosis and prognosis. Under diagnosis, we establish the working condition. Then on prognosis, we understand the operating environment. Then step number 2 on diagnosis, identify the risk and the hazard. Step number 2 on the prognosis, identify the threat of risk and hazards. Number 3 on diagnosis, analyze the risks. Number 3 on the prognosis, analyze the various contributing and leading factors. Diagnosis number 4, evaluate and prioritize the risk. Prioritize the risk for further action. Number 5, on the diagnosis, implement the precautions. Identify to minimize the risk and implement the best choice. The human rights, normally learners are asked to give the purpose of the OHS Act of 1993. So here is the answer to that one, is to provide for the health and safety of persons at work, person in connection with the use of a plant or machinery, persons against hazard arising in the workplace, and to establish an advisory council for occupational health and safety. The work ethics, I will jump the few on this topic, because as we still remember, this topic does not carry a lot of weight, but it is important for learners to read and study this question, because every mark counts. General duties of the employees to their employers. Every employer shall provide and maintain a working environment that is safe and without risk to the health of his or her employees. The employer must provide such instruction, training, and supervision to ensure the health and safety of his employees at work. The employer should establish what hazard to the safety of person are attached to any work which is performed. Then there's the general duties of the manufacturer. Any person who installs an electrical device for use in a premise shall ensure that they are safe to use. Any person who manufactures an artifact for use shall ensure that the artifact is safe and without the risk attached to it, and it has to come also with a manual of the safety use of the particular artifacts. General duties of the employees at work, I'll skip that one, but it is important that learners also read through everything under occupational health and safety. So let us start with the topic of RLC. This is one topic that will also brush it. We won't do much on it. So this topic contains theoretical question as well as the calculation. The problem with this question is that learners tend to focus more on calculations, and theory of this type of question is as important as the calculations, because at times understanding those calculations will sometimes give you the theoretical answer that you might need. So theoretical questions are normally a challenge, and many learners struggle to answer it properly. So it's important to read the theory and also practice the calculation and understand the graphs and the circuit that you are given. Learners must read all questions with understanding before answering the questions. Theoretical answer should be short and to the point. Okay, let us get to it now. Let us start with how an increase in the frequency of the frequency will affect the inductive reactance. So let us go to this particular circuit on here. If you look at this circuit, it will show you that when our frequency increase, inductive reactance will also increase, making them directly proportional. So frequency is directly proportional to our, in fact, XL, which is inductive reactance, is directly proportional to our frequency, meaning if the frequency increases, it will increase, and if the frequency decreases, it will also decrease. So let us go to the capacitive reactance. They say in capacitive reactance, when the frequency increases, the capacitive reactance decreases because the supply frequency is inversely proportional to the capacitive reactance. If you look at this picture again, it will show you that on the red one, that is XC, it will show you that when the frequency increases, that red line written XC decreases. So this one is inversely proportional, meaning it will do the opposite of what the frequency does. So if the frequency increases, it will decrease, but when the frequency decreases, it will increase. So you can even look if the frequency, if you can look at the point of series resonance there. On the lower half, where there's not much frequency, the XC is greater than the XL. Then as the frequency increase the XC decreases and the XL increases, which our XL in this case is the inductive reactance, XC being capacitive reactance. So let us go back. Then let us go back to the resistance. Normally, on the resistor does not, in fact, the supply frequency does not have any effect on the resistance, meaning when the frequency increase or decrease, it will have no barrier or any change on our resistance. So let us go. So normally there's a line here, a straight line that will be parallel to our frequency, that will show that our resistor will be parallel to your frequency, meaning no change of frequency will affect our resistance. The phase relationship between current and voltage of an AC circuit. In the inductive circuit, the current and the voltage are out of phase with each other, and the voltage is leading the current by 90. You can see that there is a circuit of, there's a pure capacitive circuit. When we say pure capacitive circuit, we refer to a circuit that has only a load of a capacitor in it. So not capacitor plus inductor in it. So in it we have a voltage leading current by 90. Let's proceed to capacitive circuit. The pure capacitive circuit, there it is. It comprises of the load, of which the load in this case is capacitor. But it's still an AC circuit. Let us see the phase relationship between the two, between current and voltage. The current and the voltage are out of phase with each other, and the voltage is lagging the current by 90 degrees. So in inductive circuit, the voltage is leading current by 90. Here the voltage is lagging current by 90. Let us go to pure resistive circuit. The pure resistive circuit is a circuit which will comprise only of a resistor. So in this case, the phase relationship between voltage and current, they are both in phase. So the phase angle here is 0 because they are in phase. You can see the waveform starts and ends at the same point between current and the voltage. Let's go. The definitions that we find here. Normally, as I've said before, learners tend to forget to study the definition, which are as important, because this is a final, and normally we say every mark counts. So let us go through our definitions. The first one, the first one is inductive reactance. What is an inductive reactance? In this case, they are saying the opposition offered by the inductor to the flow of current in an AC circuit. That's our inductive reactance. Then the capacitive reactance, the opposition offered by the capacitor to the flow of current in an AC circuit. The impedance. Impedance is the total opposition offered to the flow of current by the resultant of reactances, our reactances being XL and XC, and the resistor in a circuit supplied by AC, AC being alternating current. What is resonant? the increase in an amplitude of an oscillation in an electric system under the influence of periodic impulse of a similar frequency to the original vibrator. Normally, we say at resonance is a situation whereby in a series resonance we say XC will be equals to XL, VL will be equals to VC, and our Z will be equals to R, because XC and XL will cancel one another. Then then Z will be the maximum, which is the impedance. And under parallel resonance, we normally say IL is equals to IC. And remember here, our power factor will be 1. Because of the formula of power factor, we normally say it's R over Z. So since R is equals to impedance, our power factor will be equals to 1. And our phasor angle here will be 0. The Q factor. The Q factor, the voltage magnification that occur in a series RLC when the circuit is at its resonant frequency. The phase angle, the shift in phase between the supply voltage and the current which results from the complex circuit. Reactances, the opposition offered to the flow of current in an AC circuit by either capacitor or an inductor. That's the definition of reactance. The condition that you find under resonant frequency. Normally we say under resonant frequency, XC is equals to XL, R is equals to Z, Z is maximum, VL is equals to VC, IC is equals to IL in parallel resonance. So yes, before we go to our switching circuits, let us quickly do maybe 2 or 3 problems under this RLC. So here's the question paper here that will guide us into this question. So now we are going to try by all means to go to questions that normally give problems to learners. So here's our question paper. Then let us start with question 2. Here is the question 2. It says 2.1. There it says, explain the relationship between current and voltage in the following AC circuit. Remember here on the capacitive reactance here, initially we said they are out of phase. So we said here voltage is lagging current by 90. So voltage here is lagging by 90 degrees. Under pure resistive circuit, we said voltage is leading current by 90. Voltage leads by 90. Then going to pure resistive circuit, we said they are in phase. They are in phase with one another, meaning voltage and current, they are both in phase. So let us go to our circuit here. Normally the inductive reactance, capacitive reactance, impedance, they are normally learners, most of the time they get them right. So we'll just quickly brush those ones. We won't waste too much time on those ones. So let us see how can we go about it. Yeah. So this is our circuit. Normally we advise learners whenever they've got to write, they should put down the data that they got. So here in this case we've got R is equals to 25 ohms, then L is equals to 44 millihenries, then C is equals to 12 microfarad. Then our frequency is equals to 60 hertz. Then we go to our voltage, is equals to, our voltage is equals to 120 volts. Here we'll try to answer some of these questions. Let's go to the first one. Normally it's inductive reactance. So when we're looking for inductive reactance, here's the formula. We normally say XL is equals to 2 pi frequency multiplied by inductor. So before we can answer this question, let us remember normally our learners have this thing of forgetting our prefixes. So let us quickly write our prefixes that we normally use here. So normally we use milli with a small m. Milli is 10 to the power -3. Then milli, then we've got macro that we normally find, which is 10 to the power -6. Then we've got kilo, which is 10 to the power +3. Then the other one that they normally put, it's mega, which is 10 to the power +6. There are others, but the normal ones that the ones that are normally used are these ones. So whenever you find the milli, you know that it's 10 to the power, there's 10 to the power -3 there in the case of this in our inductor here. So let us see. As we've written our formula, there is a substitution there, which will be 2 pi. Our frequency in this case, it's 60. It's multiplied by 60 times 44 to the power of -3. So we go to our calculator here, which it will give us 16,509 ohms. So remember, if your calculation is like this, you'll get 1 mark for the formula, 1 mark for the substitution, and 1 mark for the final answer. But should you not include this ohm sign there, you'll forfeit the final mark, meaning you will get 2. So it's important to remember the signs that you are supposed to use and when you're supposed to use them. So let us proceed in calculating our XC, capacitive reactance. So XC here is equals to 1/2 pi FL. In this case, let us substitute 2 pi. Our F is still 60. Then L, our C, not L, sorry. Our C will be 120 micro. Then this is our substitution, so let us look at our answer. Then there is our answer, there is 22,11 ohms. Having these two answers, there's normally a question that learners do not normally answer it correctly as to when they ask whether the circuit is leading or lagging. Normally, the answer of that question, it lies between these two. So in this case, if we are to answer whether our circuit is leading or lagging, we've got to look at the difference between XC and XL. Now, if I'm to answer now, this circuit is whether leading or lagging, I will say this circuit is leading. leading because XC is greater than XL. So that's the reason. If XC is greater than XL, our circuit is leading. But if XL is bigger than XC, then we would say our circuit is lagging. So let us go to the impedance. So here we'll calculate our impedance, which is Z is equals to the square root of R squared plus bracket XL minus XC. This one that learners, most of them, they know how to do this one. Normally here we minus the B. We normally, because we cannot, but even if you can put it either way on the calculator, it will still give you the right answer, because we normally take a bigger number and minus a smaller number from a bigger number, so as not to get the negative number. So here in this case, from our original circuit, our R is 25 squared plus bracket our XC in this case is 22,11 minus 16,59. This is our XL, this is our XC. So our answer here will be 25,6. Yes, 25,6 ohms. Now this is the one. Now this is the correct answer. Now this is the one other mistake that our learners normally make when they've got to calculate their IT. They normally tend to use VT over R instead of Z, because in this case we are looking for the current of the whole circuit, and the current is the same, so you've got to use the total opposition, which is the impedance in this case. So our formula has to be VT, which is our total supply of the current of the voltage, over Z. So in this case we'll just substitute there. Our VT, as it has been said, is 120 over Z, which is 25,6, which will give us it will give us 4,69 amps. So this is it in this case. So normally the other thing that our learners tend to struggle with is calculating the phasor angle. So let us quickly calculate our phasor angle in this case. So just draw a line here so that we can calculate our phasor angle. Normally our phasor angle for our series circuit will say cos, then we'll say is equals to R over Z. Then as we substitute here, we'll say theta is equals to cos, then we substitute R, and our R will be 25, then our Z will be 25,6. So our phasor angle will be 25,6. So our phasor angle will be 12,43 degree. So the other thing that we must remember is doing the phasor angle whenever we are required to do the phasor angle. In this case, the phasor angle was not required, but I will do it so that the learners can see how do we do a phasor angle. So here we have our paper. Here we'll do the phasor angle. Here is our phasor angle, how we're supposed to do it. Now our phasor angle, this is how we're supposed to do it. Okay, right here, if you've got to do it with the resistors, it will be XL, XC. Then here we'll have our R. Here it is. So here to whether you do the drawings on this side or this side will also be determined by which one is bigger between XC and XL. And in this case, the bigger one, it's XC because our circuit is leading. So the bigger one is XC. So we'll do our drawing this side. We'll say this is our angle, which is 12. We have our theta here. Or if you don't want to write this theta, you can write the number, the answer that we got on the phasor angle, which in this case will be 12 degrees. So here you'll write Z, then you give the value of Z, which in this case is 25,6 ohms. Then R will be 25, XC will be 16,59 ohms. Then our XC will be 22, 22, our XC will be 22,6. Then this side, on this side you have to say XC minus XL is equals to 22,6 minus 16,59. So we've got to get the answer there. 22,6 minus 16,59. Then you'll get 6,01 ohms. So this is how you are supposed to do a phasor angle with your resistor and reactances. The same way if you have to do it with your voltages, because in a series circuit you'll have your voltages divided. So you'll have an IL, IC, then you'll do it with the currents, this one, if it was a parallel one. So normally there's normally a question that would say calculate your reactance. Now here is our reactive component. So in this case our X it's X is equals to X C minus X L. So the difference in this case it's 6,01 ohms. So this is our reactance. So let us proceed to the other parts. And let's proceed to our parallel circuit. So here they are saying 2.3, they are saying explain how the value of the capacitive reactance will be affected by the supply frequency. So as we said when we started with the RLC, the value of capacitive reactance will be affected by supply of the frequency. We said our capacitive reactance is inversely proportional to our frequency, meaning if our frequency increases, the capacitive reactance will decrease, and if the frequency decreases, the capacitive reactance will increase, so they are inversely proportional. This capacitive reactance will do the opposite of what is being done by the frequency. Frequency goes up, it goes down. Frequency goes down, the capacitive reactance will go up. So let us see here. We've got the circuit here, which we have R, we've got L, and we also have C here. So let us see here, they are saying calculate the total current. So in this case, because we are saying it's a parallel circuit, remember, they are saying calculate the total current. Here we're not going to use that formula of I is equals to VT over Z. No. Here we'll use this formula of IT is equals to the square root of IR squared plus square root of IC minus IL, depending on which one is the bigger one. So if you're going to do this, you'll get your answer. So in this case here, they are saying calculate the phasor angle. In this case, our phasor angle, we've got to do it with the currents because we do have those currents. So let us take a clean page and try to do it. Here the phasor angle, in this case, here it is, it's 2.4.2. It says cos is equals to I R over IT, the total current, if I am correct, which is the same as the IZ. So as we substitute, we'll say, we're saying theta is equals to cos, then here we'll have a substitution of IR, in this case from our circuit is 6 amps, 6 over our IT, which I did not calculate. Let me quickly do it. It's the square root, then I've got 6 squared plus bracket IL being 5 minus 4 of the IC brackets square. Then in this case we'll have 6,08 as our current, so which will have it here 6,08. So our phasor angle here will be 9,305 degree. So again, if we are to say whether this circuit is leading or lagging, we'll have to look at our current. The current there, IC and IL. So in this case, this circuit is lagging. It's lagging because IL is greater than IC. So if IC was greater, we are going to have a leading circuit. So in this case, it's a lagging phase angle. So let us proceed. Here we've got to calculate inductive reactance. The inductive reactance here, there it is. Normally, if you've got your current and the voltage, we are not going to use the same formula as the one that we normally use when we have induct or we've got capacity. In this case, we don't have capacity, the value of capacitor or the value of inductor. So we'll have to use the Ohm's law, which in this case it will be XL. Remember, XL is also it's a resistor in it. Hence, it's defined as the opposition offered by inductor in an AC circuit. So it will be XL is equals to VT over IC. We are using IC here because it's parallel, and remember, in parallel the current is divided. In series the voltage is divided. So here you'll have three different currents. But if it was a case of saying this circuit was resonance, IL was going to be equal to IC. So in this case, it's not a resonance circuit. Let us go there. We've got 240 over 5, which is our IL. In this case, it's 48 ohms. So let us look for capacitive reactance. Our XC will do the same thing because it's also a reactance. We are using the Ohm's law, which is VT over, here is IL, VT over IC. So here is because voltage is the same throughout, we'll have 120 over the value of our IC, which is 4. Then our answer in this case will be it will be 60 ohms. It will be 60 ohms. So it can go further, even to requiring the value of our R. So, but let us proceed with the rest of the question that appears here. Let's put this ones aside and go to here. Number 2.5. A parallel RLC circuit consists of 10 ohms resistor, 0.5 microfarad capacitor, and 0.2 Henry inductor connected across 120 voltage supply. Calculate the resonant frequency. Now here, if we remember the formula of our resonant frequency, here is the formula of our resonant frequency. Here is FR is equals to 1 over 2 pi square root of L multiplied by C. So here we have been given both the 2. So here we'll just substitute this 2 pi. Normally I advise learners to use pi as it is rather than writing 3,14, because normally it will be a different answer. Though it's not much difference, but there is a difference than when you are using a pi, because when you are saying 3,14, you've already rounded off. So and normally we round off to the final answer. So this over 1. Then we've got our CL, it's 0.2 multiplied by 0.05 microfarad. So in this case we'll have the answer of 1 over will be 2 0.2 multiplied by 0.5 to the power -6. Which will give us 1,591,55 hertz. This is our resonant frequency. So if you put your resonant frequency, you can be able to calculate your inductive reactance and capacitive reactance. But because these ones we did them earlier on, I will just keep this 2 and go to 2.5. Oh, sorry. Oh, we are here now. Okay, we did our frequency. Now we are going to Q factor. Q factor, normally here is the formula for Q factor. It's Q is equals to XL over R, which in this case our R was giving us 10. Where are we? 2.5.1. Our R was giving us 10. Our XL, we do the XL first. Let me quickly do this. Let's go to our formula. We'll get our Q factor, because here we are supposed to calculate the Q factor. Okay, our XL, we calculated XL earlier, which is, let's quickly scratch this one. So Q is equals to XL over R, which if you do this, it will be the value of XL, which is 1999,5 times 0.2. So this we are calculating our XL, so over 10. So if you put it into a calculator, it will give you the value of about, wait, so can I just scratch this one? Q is equals to XL over R. So here we substitute and say our XL here will be 1,999,94 over 10, which will give us 200. So this is our Q factor. So we can now proceed in calculating our bandwidth. Remember, bandwidth is BW is equals to resonant frequency over Q. So here our Q from the other side was our Q factor. In this case we got 200, then frequency was 1,591, so it's 1,591,5 over Q factor, which we got as 200. Then we'll get the answer of 7,9898 hertz. Yeah. So going back here, going back to our answers. So now I think we've exhausted this chapter as it has been done by the previous presenter, so we'll move to the chapter of the switching circuits. So before we can attempt any question on that chapter, I've got a few slides that I would like us to go through before answering any question papers. So here are the slides. So this is a chapter of the switching circuits, which we said it also consumes more of our marks, which this question weighs about 658 in the question paper of 200 marks. So what are switching circuits? Under switching circuits we find multivibrators. Multivibrators are a class of electronic switching circuits consisting of three separate types: a stable multivibrator, monostable multivibrator, and biostable multivibrator. How does one differentiate between these multivibrators? If you look at this picture that you have here, under a stable multivibrator, you do not have any input. You only have a continuous output of square waveform. So under monostable, as the word mono means one, you'll have one input or one trigger that will trigger the signal, that you'll have this signal on your output. Then jumping to biostable, as the word bi means two, you'll have two triggers. Then you'll have this waveform as your output. Here you've got two triggers, the first one being a trigger, then the second trigger being your reset. First one will be your set, then the second one will be your reset. So let us go. Let us start with the stable multivibrator. A stable multivibrator are a free running multivibrators. Its output continuously flip-flops between high and low, hence we've got this type of a waveform in it. It flip-flop high and low, and this type of multivibrator does not have any input in it. It goes on and off, because even if you look at its when doing practical for this type of circuit, there's just an LED that will flip-flop, will switch on and off continuously. So let us proceed with the operation of this stable multivibrator. Most of the times, most learners, they tend to forget this ones, and this operation of all these circuits, they take more marks. Normally it's 6 marks. At times it can even go to 8 marks. So let us go to this operation of the op-amp stable multivibrator. Here is the operation. A timing capacitor is discharged, leaving inverting input of the op-amp, which causes the op-amp to saturate and its output to rise to 15 volts, to positive 15 volts. This in turn raises the potential across the voltage pair of R1 and R2, making point B more positive than point A. When the inverting input becomes more positive than the other, the op-amp saturates in the opposite direction and its output falling to negative 15 volts. In this case is when your wave is down. it's at its negative here. Then when it goes up, it's at its positive 15. Here we'll have negative 15. Then here we'll have positive 15 on your multivibrator. When the voltage at point A has fallen below that at point B, the op amp again saturates in the opposite direction, driving its output back to positive 15 volts. This process will continue like that. This is the operation of our multivibrator being a stable in this case. So here we've got the drawing of the op amp, which will show the output waveform of this. So here is the structure. Learners also need to know how to draw this structure, and also the charging of this capacitor. Here is its waveform, then also the output waveform of this. So learners need to know how to draw all the circuits and the waveforms that you find there, either being the output and the input. Remember, in this case there's necessarily no input in this case. Remember, this a stable multivibrator, like all the three multivibrator that we normally use, they've got the op amp and the 555 circuits. So normally here you will always find 2 circuits under a stable multivibrator, which the first one being the op amp circuit and the second one being the 555 a stable multivibrator. So let us proceed. So in here we've got the 555 IC a stable multivibrator. So if you look at here, you still have your capacitor charging, then you've got your output waveform of this stable multivibrator. So without wasting time, let us go to the stable operation of the 555. The output of the circuit continuously change. Number 2, the frequency is determined by R1 and R2 and the capacitor. Then number 3, the changing ear of tree will change oscillation rate. Number 4, pin 2 and 6 connected to firing cap capacitor C allows the capacitor to oscillate. Remember, in this case you've got to, they said we must get to the point, so write the points only when you've got to answer these types of operation, and look at the marks allocation, because normally these operations of this type of circuits, they require a lot of marks. So normally it's 4 or 6 at times. So it's important for learners to know all the operation of these multivibrators. So in here we'll have a monostable multivibrator. It produces 1 pulse cycle of high and low when trigger pulse is applied. So this one being a monostable multivibrator, it only consists of one trigger pulse. So this trigger pulse will make it will lead the circuit to be high, and when you press it again will make the circuit low. This is our op amp monostable multivibrator. Then let us go through the operation of the op amp. The operation says when the circuit is in its natural condition, a negative voltage of the VRF serves to hold the op amps in the inverting low. The capacitor charges up with its top plate at positive 15 volts and its low plate at 0 voltage. When a trigger pulse is greater than VREF applied, the op amp will reverse and saturate to negative 15 volts. So this is the operation, and here is the 555 circuit. Remember the one that we just gone through is the operation of the op amp, not the 555. So here is the 555, here is the trigger pulse, and there's the capacitor charging, and this will be our output. So it's important for learners to know how to draw these circuits. So let us resume to the operation of this 555 monostable multivibrate. Number 1, pulling pin 2 down to 0 triggers the 555. That's point number 1. Then point number 2, pin 2 is connected to a series R2 coupled to VCC plus voltage, which is point number 2. Number 3, it says a push to make switch is coupled to the ground, which is 0 voltage on the ground. Number 4, the pull-up resistor keeps pin 2 at high. Number 5, it says the circuit will be in its steady state. So this is your operation of the 555 IC monostable. Then in here we've got a biostable multivibrate. Then remember this one, it has 2 triggers. The first trigger being the set, the second trigger being the reset. So let us go through this one. A circuit that has 2 stable states, either high or low, whether a trigger pulse is received. There is a circuit of op-amp multivibrator, biostable, and here is the input with the spikes, then the output with the square. If you look at the output here, the output is inverting output here because it starts high, or else the input starts lower. So normally if it's like this, we say inverting. If the other one, because normally if we are to go back to the logics, we'll say this is 0 here because it's low, then this is high, it will be 1. So if the input and the output, they are opposite, normally we refer to that as the inverting. Then the operation of op-amp biostable here is as follows. The op-amp operates as a comparator. A capacitor cannot charge instantly. If volt is high, then the non-inverting input terminal will be smaller. Changes states when trigger pulse is applied. It has 2 states. Those 2 states being either high or low. Normally we refer to this now when we go back to our logic, we refer to 1 as high, then 0 as low. And also we can refer to this as being on and this one being off. Then here we've got 555 bistable circuit diagram. Remember in the beginning of this chapter we said in every multivibrator we've got 2 circuits. The first one being the op-amp and the second one being the 555. So here in this case we've got the 555 IC bistable circuit diagram, and we also have the trigger input, the reset trigger, and we've got the output. Now here it's what we were saying when we said it has a trigger and which is the set and the reset. Here you've got a set which is trigger number 1, then trigger number 2 it's a reset which is normally connected to pin number 4. So you should be able to draw this type of a circuit. Then let us proceed to 555 IC bistable multivibrate operation. So here they are saying resistor R1 and R2 are called pull-up resistors, here in this case it's your resistor 1 and resistor 2. They are referred to as the pull-up resistors. Both set or reset switches open the resistors and they connect their input and positive power line. Without these resistors, the circuit will be floating. Pressing the set switch will pull pin 2 low and cause the IC output to flip and rise high. So in this case of the circuit, if normally you switch on the set number 1, you will have a high output in the side. If you reset, your output will go back to 0. So with that said, let us proceed to our schematic trigger. For every circuit that we come across, learners need to know the type of circuit and the operation of that circuit. Hence, there's always an operation for every circuit that we do here. So before we just this is a schematic trigger circuit that learners also need to know how to draw. Let us go on to its operation. The circuit uses positive feedback. The circuit uses positive feedback with V out being divided through R1 and RF being RF we refer to feedback resistor to produce a small fraction of voltage. If there is a generative feedback on the circuit, the output will hold until the voltage on the inverting input rises higher than that on the non-inverting input. The output remains in a constant state until V in rises and equals to V out. This is the operation of our schematic trigger circuit. Then here is the applications where we normally find this schematic trigger. We find the schematic trigger on the analog to digital converter. A signal can be recovered. It is used in the first stages of radio receivers, varying input waveforms. So this is our application of our schematic triggers. Proceeding here, we'll have 555 schematic trigger circuit. Here is the 555 schematic trigger circuit with the input waveform and also the output waveform. With this one sine wave being the input and the square wave being the output waveform of the 555 IC schematic trigger circuit. The use of the 555 timer as a schematic trigger is shown in figure that is on top there. There are two internal comparators are tied together and external. Okay, this is not that important. Let us go to the comparator. The comparator operation. 1 mega. Look at the resistor from the voltage divider network. The voltage across is serving as reference voltage. The input voltage at V1 is compared with VRF across with the different being amplified. The circuit amplifies the difference between V2 and VREF. This is given as 0 output. This is the operation of the comparator. Then in here we've got the comparator applications. It is used as a light fall. LDR rises to at non-inverting input also rises. The op-amp output will go high, activating the output. The temperature sensor, we use it as a temperature sensor. Normally at low temp, when it works as temperature sensor, at low temperature the Mr. R is high, causing the V at inverting input to be low. At high temperature on the op-amp will work when the second reference V is triggered. Here is the summing amplifier. We'll also go through the calculations of the summing amplifier later on. Here is the summing amplifier circuit and the operation. So here we go. Here there are 3 resistors which govern the circuit gain, which are the circuit, the R-ins. Then the voltage at the inverting input is controlled by the feedback resistor loop. The voltage on our inverting, here are the 3 voltages that on the inverting. Then the feedback resistor maintains minimal difference between the op-amp inputs, which in this case is our RF. The summed output will be negative. Input voltage amplifies the signal voltage to ground, which is 0 volts. The differentiators. Here we've got our differentiator input signals and the output signals. Normally we say if your input is a square wave, your output will be spikes. As you can see here are those spikes. If your input is a triangle, your output will be a square wave, if you can see well here. And if you look at the two, this one of the square wave and the spikes, they are in phase, and the triangle with the square, they are also in phase. So let us go to the last one of the sine wave. Normally if you've got a sine wave, your output will still be a sine wave, but with a phase difference of 90 in this case. So as you can see where this wave starts on the input, it starts down at 0, then here it starts up there at 90. So there's a phase difference of 90 degree. Then let's go to the operation of the differentiator. When the input is a positive going in voltage, a current flow into the capacitor. Since the current flowing onto the op-amp is 0, effectively all the current flow through the feedback resistor. Then here we've got our op-amp differentiator. Understanding that there are many of these circuits, so it is important that learners remember all these circuits and their operation. Then proceeding to the integrator, the op-amp integrator. There we've got our circuit, which is integrator. Here on top is the integrator, then below here is the differentiator circuit. So yeah, if you look at the difference between these two circuits, the integrator and the differentiator, you'll see the difference here. It's just the position of the resistor and the capacitor, and also the input and the output. Here if you look at this, your resistor in this case, which is your RF, your R, it's here on the input, whereas if you look at your differentiator, on your input you've got your capacitor. Then here our feedback, it's here. In this case here you've got a capacitor, this is being our feedback resistor. So also the difference is our input and output. On the integrator you've got the input of square wave, the output being triangular. Then going to a differentiator, it will be triangular on the input, square on the output. Then here is the op-amp integrator operation. It says when a constant current is fed to a capacitor, it will charge at a constant. The op-amp's two inputs are viewed as both possessing the same voltage always. The op-amp inputs draw 0 current, so any input current is passed through to feedback current. So this is the end of the topic of switching circuit. So now we can go through the one question paper and see if we can get any answers. Here it's our switching circuit, which is normal question 4, which is out of 58 marks normally. So let us see the first question. It says, explain the purpose of an unstable multivibrator. So in this case, the purpose of a stable multivibrator is that it generates a continuous series of pulses without the need of the trigger pulse. Remember, we said the unstable multivibrator does not have any input. It produces a continuous low and high pulse in the output. So let us see here, they are saying draw a label circuit diagram of 714 multivibrators. So if you remember this one, we went to on our previous we went to this one, and we discussed the importance of knowing how to draw and label this circuit. So this is it's not a very difficult circuit to draw. If normally you've got to draw it, and here they specified it has to be 741 op amp. So normally you'll have your op amp here, then here you'll have this, which will be connected to your resistors R1 and R2. Then in here you have your V out. Then in here you've got your feedback resistor, which is RF. Then in here you will have your capacitor, which will go back to our ground and R2. So here you've got your V out, which is 0 because it's on the ground. Then here you've got your R1, R2 I mean, and here is R1. It's very important for us to label this type of a circuit, people, because they said a labeled circuit. Well, it's 15 normally, here it's negative 50 volts, here it's positive 15 volts. So this is our 714 unstable multivibrator circuit that should be drawn, and normally your sketch sheet should be as clean as you can. So let us proceed to the next question, which says refer to the figure 4.3, which is this one below, and answer the question that follows. So the first question, it says there is the function of R1 and R2. So normally this is your R1, this is your R1, and this is your R2. This, by the way, it's a biostable multivibrator. How do you see that this is a biostable 555 multivibrator? You will see by these two triggers, the other one being set and the other one being the reset. It's a giveaway that this is a 555 biostable multivibrator. The 555 you'll also see by this type of IC, which will written 555 inside. If it was an op amp, it was want to have your op amp as a symbol of a triangle, but because of it's a square with the 555, it's a giveaway that this is in fact a 555 biostable multivibrator. So let us see 4.3. It says state the function of R1 and R2, which are those two at the top there. So normally we say resistor R1 and R2, we call them the pull-up resistors, which will be a mark for saying R1 and R2 are pull-up resistors. Then resistor R1 and R2 will hold both trigger pin 2 and the reset pin 4 at high. So it's another mark which will have 2 marks there. So we say 4.3.1 R1 and R2 are pull up resistors. Then we say resistor, okay, R1 and R2 will hold both trigger pin 2 at reset pin 4 high. So here you'll have 2 marks for this answer. So let us proceed. So if the time still allows us, we'll also look at the amplifier, which is one other question that normally the learner struggles with. Here they say, describe what happens when the set switch 1 is pressed. Normally, let me explain this in a simple way. Normally when you press switch 1, you'll have your LED will light if you have done it practically. So but the answer for that one, you've got to put it in a way that will justify the 3 marks that is being put aside as the allocation there. So normally if they say the trigger pin 2 will be pulled low if the S1 is pressed and cause the IC output to flip and rise high, turning the LED on when the set switch is pressed. So that's your answer. But if I may continue about pressing the reset 2, if you are to press the reset 2, it will reset the circuit will go back to reset, everything will be off. So I hope you've got the answer of 4.3.2. 4.3.3, it says explain why threshold pin 6 is connected directly to the ground. The threshold pin 6 is purposely held at 0, causing the IC to reset, keeping the output high when S1 is pressed. That is our answer for that one. Now here on number this is number 4.4. They are saying figure 4.4 below show input trigger pulse of A and B 555 monostable multi-vibrator. So this being our trigger pulse and this being our capacitor charging. So in this case we have to draw, the answer says draw the output signal of the answer sheet here, our output signal. So we just have to normally project. So I'm going to draw my pulse. So here is how my pulse is going to be. I'm going to have here low, and here it will go up, then it will be at rest up until it goes low again, and it's at rest, then it goes up, then it goes at rest, then it goes low, then it's at rest again. Then this will be our output. Normally if you have got this, it's normally the same as this one, but the output will be your square, which is the opposite of this of the trigger pulse, because when the trigger pulse is at high, the input will be at low, and when the trigger pulse is at high, well, I said when the trigger pulse is at high here, the trigger pulse is at high here, this will be our 0, Now in the same position, our input will be at low, which is 0. Then when it comes low to 0, the input will be high, which is inverting in this case. So here is our answer here. So let us go back. Describe the condition that occur at trigger pulse B. Here it says the duration of time of a trigger pulse B will not influence the condition of the circuit, and for that reason the charge temp of the capacitor will not be influenced. So here they say number 4.4.3, they say explain why the condition that occur at trigger pulse B does not affect the capacitor charging. You are saying the output signal represent an inverting schemic trigger because the input signal is inverting with reference to the input signal. Or if you can say that, you can also say the input signal is at VEE when triggered by the upper trigger voltage and swings to positive voltage when triggered by the lower trigger voltage. And here we go to 4.5. 4.5.1. It says states whether the output signal represents the inverting or non-inverting schemic trigger. Motivate your answer. Here you've got to look at the phase difference. Here the phase difference, you look at the phase difference. If they are starting on the same way, then it's non-inverting. But if there's a phase difference, then it's inverting. So in this case, the output represents the inverting schemic trigger, because the output signal is inverting with reference to the input signal. Then let's move to number 4.5.2. Draw the circuit diagram of a schemic trigger consisting of 2 resistors and a 741 op-amp that will produce the output signal in figure 4.5.1. Remember, schemic trigger, you also, in this case, they specify as to which circuit do they want. As they said, they want the op-amp. Normally, the schemic trigger has 2. It has the op-amp and the 555. So the op-amp one, it's actually easier, as you'll have your op-amp here. Your op-amp here, which is your V out. Then you'll have here VE minus and plus, and in here you have plus VCC, and in here you'll have your negative VCC. Then here you'll have your RF, which is your feedback resistor. Then here, parallel to it, you'll have your R1, which is connected to the ground. And here you look at your 0V, then V out, V in here. With this, you'll get your full 7 marks, because they set 2 resistors, the other one being your feedback resistor, and this one will be your resistor number 1. Then if you can be able to draw this, you can get your full complementary of marks as advertised by the question. So let us proceed. In here they are saying name two transducers that can be used in an input device to schematic trigger. If you remember, in grade 11 we did a chapter called sensors and transducers. So this question refers you to the grade 11 that we did thermocouple, we did microphones, we did the piezo sensor. So if you mention any of those, then you'll get your marks. So in here it says throw the input signal, throw the output signal of this circuit. So in here the output signal, I'll just do it here with this one. So the output signal will be higher up there, then it will go down, then as this one is, it will also rise. So this one will rise as the other one, as the input rises, and it will fall as the input falls. So for this you'll get your full marks. You've got to write here your output, then you can get your full marks for drawing this circuit. And you also have to write here minus V, which is 1, then plus 1V. You'll get your full marks for drawing and labeling the circuit. And let's proceed. Now we are proceeding to 4.6. Here is the circuit there. It says 4.6.1, identify the op-amp circuit diagram in figure 4.6. Identify the op-amp circuit in figure 4.6. The circuit here is the comparator. This circuit is the comparator, so if you are saying the comparator, you will get your full marks, or the inverting comparator. In fact, you're supposed to say the inverting comparator, because if you're saying comparator only, you'll get only 1 mark. So say in full inverting comparator. So in here, number 4.6.2, they say draw the output signal of the diagram on top there. On the sheet 4.6.2. Let's look at the sheet. We're supposed to do the, okay, here is the sheet. Here we are supposed to do the output. They already gave us the input, so in here you'll have a square. It will be like this. So it's actually the opposite. If this one is high, this one will be low. So if this one rests on low, this one will rest on high. So let us proceed. In here they are saying explain how the reference voltage is made negative. Change the connection of resistor R from the positive supply to a negative supply. If you change R1 from positive and put it on the negative supply, then you'll have negative voltage. Then in here they are saying below answer the question that follows. So in here we've got our circuit. So let us put the data down. So here they have V1 is equals to 300 millivolts. V2 is equals to, so if you want to write them in decimal, you can always divide them by 1000. So here I'll get 0,3, here I'll get 0,5 volts, here I'll get V3, I'll get 0,4 volts. Then my RF will be 100k. RF is equals to 100k kilo ohms, which is 100,000 if it's like this. Then R1, R2, R3, they are all the same. So R1, R2, R3 is equals to 20 kilo ohms, which is equals to 20,000 ohms in this case. So let us calculate this. So, okay, before we calculate, there is a question which says, explain how the gain of this amplifier can be determined. So normally we say the gain of amplifier is determined by the ratio of the feedback resistor to the input resistor of each branch. So in here, the following one will say, calculate the output voltage of the amplifier. So remember the formula here, it's V out, because it's output, V out is equals to negative, if you this it's in here. Let's just look for the formula just to make sure. Okay, switching sequence formula. Okay, the formula is not here, but we know the formula for this one is negative bracket, then we say V1 over RF over R1 plus V2 multiplied by RF over R2. Then it will continue saying plus V3 multiplied by RF over R3, R2. Remember, all our R1, R2, R3, they are all the same. So here we are going to substitute. So it's a minus, then here, as we wrote them there. The first one, the V1, we've got 0,3 over RF. Our RF is 100,000 ohms over 20 kilo ohms plus V2 is 0,5. Here RF is still the same, it's 100k over R2 is still 20k plus R3 is 0,4. Here will be 0,4 over RF is still 100k over 100k over 20k in the brackets. So I ran out of space there. So in here, if you put this in your calculator, yeah, let me just quickly put it in a calculator. It's negative, open brackets, then in here we'll have this, we'll have 0,3 multiplied by 100,000 over 20k plus 0.5 multiply by 100k over 20k plus 0.4 of R4 multiply by 100k over 20k, in the brackets the answer will have -6 volts. So for this calculation you'll get your full complementary marks of -6 marks. So we proceed. We're saying give a reason why the amplifier is not saturated. The reason is that the gain of the amplifier is determined by the ratio of the feedback resistor to the input resistance of each branch. Oh, sorry, I'm on to 4.7 now. 4.71. Well, the amplifier is not saturated because the output voltage is less than the supply voltage. So the output voltage is less than the supply voltage. That's the reason why the amplifier is not saturated. So the second one, it says calculate the gain of the amplifier using the voltage values. So in here they are saying we should calculate the gain using the voltage values. Let us look at the formula sheet and see if we've got the formula for that one. Okay. In this case it should be this formula. Okay. Because we just calculated the V out, so we'll have a V out. So our formula will say gain is equals to average is equals to V out over V in. So if you go back to the circuit here, going back to the circuit, we've got these three input voltages, so we've got to add them. So in here we've got -6 over 0.3 plus 0.5 plus 0.4. So if we put it in a calculator, it will give us should give us -5 volts. That's the answer for 4.7.4. So this is our answer for 4.7.4 that we were supposed to calculate. We're supposed to calculate the gain of the amplifier using the voltage values. Let us proceed to the last one in this question. Here they say describe what will happen to the output voltage if the value of R2 is changed to RK to 10k, which is 10,000 ohms or 10 kilo ohms. So if R2 is changed to 10k, the gain of V2 will increase, causing the total output voltage to decrease. So the total voltage will decrease. So let us proceed in here to an amplifier. Hopefully we still have some time left on us to do this chapter. Of the amplifier theory. There is the amplifier theory here. So amplifiers, normally when we go to this chapter, majority of this chapter was done in grade about 25% of the questions that are normally asked here are done in grade 11. So it's very important for learners to remember what they did in grade 11 on this chapter of the amplifier, because those maybe 4, 5 or 6 first questions, which normally makes up of 25% of this, the marks of this question, are the stuff that they did in grade 11. So here, let us go in with this one. In here it says amplifier theory. Then you've got a pre-amplifier. It produces high current gains, which is your small signal amplifier. It is used to enlarge a very low level signal of the voltage. You've got two types of amplifiers in this case. You've got small signal amplifier, and you also have the power amplifier. Now this one, they say, produces high voltage gain to a more manageable size. So it normally takes to a smaller, it takes from a smaller signal that cannot be detected by the power amplifier, then will amplify it to a manageable size. It is normally used in pre-amplified stages to boost the signal to a larger level before passing it on the power amplifier. So basically here they are saying for the power amplifier needs the small signal amplifier to pick up the smaller signal to put it into a manageable size so that it can amplify it to the right size to be picked up by the power amplifier, because power amplifier cannot pick up a very small signal. It needs a manageable one. So here is the power amplifier. They are saying it takes a larger signal at its input and boosts it to a larger sufficiently high power gains level as to drive a loudspeaker. Transistor biasing. A transistor is said to be biased when its surrounding circuit set up to the correct voltages at its terminals. This is your input and output of the characteristic curve of your transistor. This one being the input, this one being your output. Normally this is the stuff that was done in grade 11, so just a reminder of those things that were done in grade 11, because they are normally as this stuff. Now here we've got a quiescent point. Before we go here, let us go to the load line, because the quiescent point goes hand in hand with the load lines. So normally when you draw a load line, I can make an example. Let me see if I've got any question in here that will lead us into this. In here, before we go to the quiescent point, in here we've got the circuit of the amplifier, whereby a learner is required to get the maximum current, because you need that maximum current and the VCC to draw the load line. So let us first do 5.1 and 5.2 so that we can do the load line. So normally they are saying at 5.1 they are saying calculate the value of VCE. Normally we say when your circuit is off, we're saying VCE is equals to VCC. So in here VCE is equals to 12 volts as it is here on our circuit. So in here we've got to do the maximum current, or Imax, which is IC is equals to VCC over RC. So in here we've got VCC of 12 volts over 1000, which is our RC, collector resistor. So in here, if you put it in the calculator, you'll have 12 divided by 1000 which will give us 0,012. If you want to convert this number to with a suffix of a milli, you will say this multiplied by 1,000, which will give us 12. It will give us 12 milliamps. Because the current is it's very important to remember to include A, which signals the it's a milli. So in this case, if you've got this answer, it will be easy for you to get your load line, because your load line is your maximum current by your maximum voltage. So in here we'll have our IC in milliamps. Then here we'll have our voltage. So in here the maximum there is 12. So in this case as well is 12 milliamps. So you'll combine these two lines. So normally, if this circuit of us it's of a transistor of class A, our quiescent point will be right in the middle, towards the middle. So in here we'll have our quiescent point for our class A amplifier. So there are certain questions that they normally ask. They would sometimes ask what will happen to the supply current if VCC is increased. Normally, current in Ohm's law, we say current is directly proportional to our voltage. So if our voltage increases here, it simply means even our current here will also increase. But if our RC increases, our current will drop. So it might drop to somewhere here. Just making an example, it might drop to somewhere here, which will also shift the quiescent point. So with this stuff out of the way of the load line, let us proceed to the next level. Let's put the question paper aside a bit. We continue to the quiescent point. Let's proceed to our time is almost over, so we've got to run quickly here. The point at which two overlaying graphs intersect a transistor biasing circuit is designed to its purpose. Set the transistor operating condition. Let us quickly go to the classes of the class and the operation of this class A. Class A biasing. A quiescent point chosen to lie in the center of the active region. Normally, as we will remember that our transistor has three regions as an amplifier. You've got saturation region, you've got active region, and you also have the cutoff region at the bottom. So it conducts for class A will conduct for a full 360-degree angle. The advantage of this is that maximum undistorted swing of both V out and input are possible. The disadvantage is that the transistor draws its full biasing current even with no input signal present. Application: where do we find this? It is used in pre-amplified circuit. Frequency response: the frequency at which the amplifier circuit will respond without distortion. Now here it's the circuit and the load lines and the Q point of our class A transistor. Then let us go to class B biasing. This one, it conducts for 180 degrees of the input signal. The Q point right at the bottom of the of the load line. If you can see here is our Q point here at the bottom of our load line on the cutoff region there. The advantage of this is that the transistor remains in its cutoff region, drawing no current when there is no input signal introduced. This advantage is that it can't amplify audio input signal itself. The first 0.7 volts of any input signal must overcome the depletion region of the B junction. Here is the circuit as we've said. Then let us go quickly to class C. The class C biasing, it conducts for less than 1/2 of cycle of the input signal, 180 degree. The application is that it is used in a 10 RF amplification circuit, and here is the circuit and the load line with the Q point at the bottom there. Then the class AB, it conducts more than 180 but less than 360 of an input cycle. Advantages of this is that the circuit is almost as efficient as class B. The circuit introduces little or no distortion. Each half is able to amplify the input signal to double its greatest size. Application, it is used in audio power amplifier. Now here, let us go to the amplifier feedback. Now on the feedbacks, we've got two types of feedbacks. The first one being positive feedback, and then the other one being the negative feedback. The positive feedback, it says when the signal feedback is added to the input, then when it's added, you've got a positive. The negative, when the signal feedback is subtracted from the input signal, then you've got your negative. This is your circuit of feedback amplifier. Now this circuit is used for both input and output as it is. Normally in grade 11, when we were drawing this circuit, whenever it was a negative feedback, we would put negative in here, but when it was positive feedback, will indicate with a sign. So with this here, we don't necessarily have to indicate whether it's a positive or negative. Now the advantages of negative feedback. Yes, just going through it. The advantages of negative feedback: it improves the stability of the amplifier, increase the amplifier's bandwidth, reduce the produced noise within the amplifier, enhancing the amplifier input and output impedance. The disadvantages: by introducing the feedback loop to an amplifier, its overall input and output gain is reduced. The last part, the effects of negative feedback: gain, stability and bandwidth, distortion and noise. Unfortunately, we've run out of time, so this is it. We'd like to wish all the matriculants the best of luck in this paper of electronics. So thank you.